Hello students, welcome to Sri Jayendra's Rank Zone classes. I'm your friend and mentor for coming classes with respect to physics. This is lecture number 1 of a unit semiconductors. So let's begin with today's class. In today this is the introductory session of the semiconductors. But before we switch on to the semiconductors, let's have a little look at the world before semiconductors too. Before we were using the semiconductors such as the diodes and transistor and all this stuff which is used in today's world, we are having a vacuum diodes, and that vacuum diodes has two electrodes, and these two electrodes are named as the anodes and the cathodes. And after the vacuum diodes we are having the vacuum tubes. Generally they are said as a vacuum valves too, and this vacuum tubes or vacuum valves could be categorized in two segments. It's a vacuum diodes and vacuum triodes. Diodes, as its name suggests, that it is having the two what we can say two terminals or two anodes. One is the cathode, another is the anodes. And vacuum triodes has three terminals that we call as a cathode, plate and grate. Same way we are having the tetrodes too, which is having the four electrodes, as well as the pentodes, which all are having the five electrons. So basically what valve is, what do we understood by the valve? So when we say it's a valve, we understood that it is a devices in which a controlled flow of electrons can be obtained. Controlled flow of electrons can be obtained are the basic building blocks of all the electronic circuits. When we say controlled flow of electrons, that means when we wish a current should flow, ideally an electron should travel, and when we wish that current should not flow, then current should stop. This is what we understood, and this is what our requirement when we say it's a controlled flow. In a vacuum tube, the electrons are supplied by a heated cathode, and controlled flow of this electron in vacuum is obtained by varying the voltage between its different electrodes. So this is how vacuum tubes and electrodes and that all the previous versions of the semiconductor diodes and transistors were working. Now what are the limitations? Let's have a look. And what are the incapabilities of this diodes? First, a vacuum is required in the inter-electrode space. Otherwise the moving electrons may lose their energy on collision with the air molecules in their path. So every time when you want to use it, you need to create a vacuum over that region, and that is not possible every time to create a vacuum and use it. Next, in this devices, the electrons can only flow from the cathode to the anode only. That means only in one direction. Therefore, such devices are generally referred as a valves, and it is even not possible to have a reverse or change the direction of the current. That is the second limitation. Next, this vacuum tube devices are bulky. This is the biggest disadvantage of this devices. They consume a high power, second limitation, and they operated generally at a higher of voltage, it's a 100 volt, and have limited life and low reliability. So these are the limitations of this valves. And because first thing, they are the bulky, so they are not going to accommodate themselves in a shorter space or a smaller space, which is the requirement of nowadays. Second, it is having a limited life. When we say it is having a limited life, that means it is going to fuse every now and then. That means you need to appoint a one person who is responsible to change all those valves that has been fused. Yes, so this is the another disadvantage. And next is the low reliability. Once you install it, you are not rest assured that this is going to work fine. No. So this all are the challenges, or this all are the, we can say, limitations of this previous times valves and electrodes. Yes. So now what we wish, or what is our requirement when we use semiconductor. So these are the certain list of this requirements, or this should be done, this should be done. Let's have a look. So semiconductors, there should be no external heat or large evacuated space is required. Yes, we are not going to have every time the large evacuated space from where I'm going to release the heat. It should be small in size. It should consume low power. It should be operated at low voltages. One most favorable, it's a long life and high reliability. When we say CRTs, that are the cathode ray tubes and computer monitors, which work on the principle of vacuum tubes, are now replaced by the liquid crystal display, which we call as a LCD. In a nowadays, even the LCDs are no more there, and we used to have at our home too. It's an LED, light emitting diodes, as well as plasma TV, and even now we have moved beyond even the LEDs and plasma. Yes, what not is available. So this all is due to this evolution in the semiconductors, and we are going to see this evolution one by one step. So we have begin our discussion with the valves. Yes, and then we are on a next phase from valves to diodes to PN junction diode to transistor, and so on. Let's have certain quick questions. The question is, devices in which a flow of blank can be obtained are the building blocks of all the electronic circuits. Yes, devices in which a flow of electrons can be obtained are the building blocks of all the electronic circuit. Next, vacuum tubes. Vacuum tubes are replaced by, yes, tubes are replaced by the semiconductors. Now, let's classify it. Let's classify the solids. It's a classification of solids. So basically, when we classify the solids, one of the approach to classify the solids is, one of them is the crystalline solid, and the second one is the amorphous solid. So what crystalline solid is, let's have a look. When we say crystalline solids, in that the atoms or molecules are arranged in regular periodic geometrical pattern over a longer range, such as the sugar, a quartz, mica, calcite, sodium chloride, or diamond, etc. All this are the examples of the crystalline solids. And when I say crystalline solids, they are the anisotropic. Now, the question may arise that what does anisotropic mean? When we say anisotropic, it means that the physical properties like thermal conductivity or elasticity or electrical conductivity or refractive indexes, mechanical strength are different in different directions. That is what we understood, and that is what we call as an anisotropic. So they are having different properties. They behave differently in every different directions. This is what we call as an anisotropic. They are bounded by the flat surfaces, and they are having a sharp melting points. So this was the crystalline solids. Now let's have a look what amorphous solids is all about. When we say amorphous solids, in amorphous solids, the atoms or molecules are arranged in an irregular pattern. And when we say that this are arranged in irregular pattern, that means a rubber, glass, plastic, sulfur, etc. are the examples of the amorphous solids. And we can say amorphous solids are the isotropic. When I say isotropic, it means the physical properties are same in all directions. So in anisotropic, physical properties were different in different directions, and in isotropic, the physical properties are same in all directions, and they do not have well defined melting and freezing points. This is what we call as an isotropic, and this is the amorphous solids. Now let's classify the solids based on their electrical properties. This is the second way to classify the solids. This is based on the electrical properties. So we are going to divide them into conductor, insulators and semiconductors. And let's begin our discussion with the conductors. So conductors are the substances which easily allow the electric current through them, are called as the conductors, such as the AU, gold or silver or copper or aluminum, or we can say all metals. All metals are the considered as the conductors. So for the conductors, electrical conductivity is very high, approximately 10 to the power 2 to 10 to the power 8 units. And their electrical resistivity is low. Its resistivity is equals to 1 by conductivity, which is approximately 10 to the power minus 2 to 10 to the power minus of 8 ohm into meter. The temperature coefficient of resistance, which we call as an alpha, which is positive. Next is the insulators, and insulators are the substances which do not allow the electric current through them. They are known as the insulators, such as the rubber or plastic or wood or glass, etc. are the cases of the insulators. Insulators conductivity is low. Yes, exactly opposite to the conductors, which is approximately 10 to the power minus of 11 to the 20 to the power minus of 19 units, and the resistivity is very high. When we say its resistivity is high, that means it's 10 to the power 11 to 10 to the power 19, and the temperature coefficient is negative. I hope you understand what temperature coefficient negative means. That as soon as you increase your temperature, as soon as you are as soon as you are going to increase your temperature, your resistance is going to decrease, and vice versa, the same is true. I hope this is clear. Now let's discuss very important it's in semiconductors. So they are the substances whose electrical properties lie between the conductors and insulators, and they are known as the semiconductors. The examples of the semiconductors are the germanium, which is atomic number 32, silicon, atomic number 14. The properties of semiconductor is that electrical conductivity is higher than that of the insulators, but it is lower than that of the conductors. So basically, if I arrange them into a certain orders, then conductivity of conductor is greater than the semiconductor, but conductivity of the semiconductor is greater than the conductivity of the insulators. So its conductivity is higher. Next, their electrical resistivity is higher than that of the conductors, but it is lower than that of the insulators. So when I say the ranges, when I say the sequences of the resistivity, then resistivity of insulator is greater than the resistivity of the semiconductor, and which is greater than the resistivity of the conductors. And the resistivity lie in the range of 10 to the power minus of 5 to the 10 to the power 6 ohm into meter. Temperature coefficient of resistivity is negative. So let's look at this. The graph shows all of this, that relation of conductivity versus the temperature. As you can see that as soon as temperature increases, the conductivity of the conductors decreases by a little. Yes, for semiconductors and insulators, as soon as temperature increases, as soon as temperature increases, their conductivity increases. Yes, I hope this is clear. Is it clear? Any doubts up till now? Is there anything? No? Great. Now let's classify the semiconductors. So basically semiconductors can be classified into two segments. One is the elemental semiconductors and other is the compound semiconductors. When I say elemental semiconductors, they could be of two. The one of them is the silicon, another one is the germanium. And when I say it's a compound semiconductors, that could be again classified in three segments. It's an inorganic, semiconductors, organic semiconductors, or we can say organic polymers. These are the examples of the inorganic semiconductors, and these two are the examples of the organic and organic polymers semiconductors. I hope this is clear. So this is how we can classify the semiconductors. I hope this is clear. Is it? Great. Now let's have certain quick questions and then we will go to the band theory. First, the question says atoms or molecules are arranged in regular, periodic, geometrical pattern over a long range. These are the crystalline solids. Next, the physical properties which are different in different directions are termed as the anisotropic. Next, silicon and germanium. Silicon and germanium are the semiconductors. Yes. So now let's look at the band theory of solids. This is one of the very important aspect and very important approach to understand that how each element is going to behave every year time, whether it could be of a normal situation or if temperature changes and how this will behave. Let's have a look what it says. So when I discussed band theory of solid, it was according to the Bohr's theory of atomic spectrum and the concept of electronic configuration. There are well defined discrete energy levels of electrons in an isolated atom that you understand. Yes, this is the part of the chemistry that you learn very well. It was the, if I if we discuss the different energy levels, it's a 1s, 2s, 2p, 3s and onwards, and this all are the energy levels for an isolated atom. If you understand it from here, it's from the center, from it's a 1s, this is 2s, this is 2p, this is 3s, this is 3p and onwards. Yes, so these are the discrete energy levels where electrons can reside, and an isolated atom are brought together to form a solid crystal, and various interaction occur between the neighboring atoms. Due to this interaction, there is no appreciable change in the energy levels of the inner shell, but the higher energy levels are considerably affected, and without violating even Pauli's exclusion principle, there is a change in the energy levels. So there will be a splitting of a single energy levels of an isolated atom into a large number of energy levels for atom in a solids. So if I classify this or if I divide this, then we are having on the upper side, they are the bands. That is what we call as a conduction band, and the lower bands, they are the known as the valence bands. And the difference between this two, a difference between this is what we call as the forbidden energy gap. When I say conduction band, all the electrons they are ready to conduct are reside within the conduction band, and all the electrons they are not about to conduct, they all reside into the valence band. And there is a difference between these two levels, and that is what we call as the forbidden energy gap. That forbidden energy gap is different for different element that we will see. So first, let's have a look. It's inside the crystal, each electron has a unique position and no two electrons see exactly the same pattern of surrounding changes. So because of this each electron will have a different energy level, and this different energy levels with a continuous energy variation form are called as the energy bands. The energy bands, which includes the energy levels of the valence electrons, this is what we call as a valence band. And the energy band above the valence band, the energy bands above the valence band is called as the conduction band. With no external energy, all the valence electrons will reside in the valence band. So if the lowest level in the conduction band happens to be lower than the highest level of the valence band, Yes, this was the a case of the lowest level of the valence band. And if there is a some gap between the conduction band and the valence band, electrons in the valence band all remain bound, and there should be a no free electrons are available in the conduction band. And if it is the case, then this makes the material an insulator where no conduction, where no electrons are there which is going to conduct. I hope this is clear. Now let's look at this, what forbidden energy gap is. So forbidden energy gap is the energy gap between the valence band and the conduction band, and this is what we call as the forbidden energy gap. So no electron will exist with an energy level in the forbidden gap, and the minimum energy required at 0 Kelvin to produce electron hole pair in a semiconductor is equals to the forbidden energy gap. I hope this is clear. Let's view this diametrically. It's a diagram of the, this are the fields, this are the empty. As you understand, this is my valence band, this is my conduction band, and the difference of this levels between these two is the forbidden energy gap. So the energy band position in a semiconductor at 0 Kelvin, this is the diagram for the semiconductor for 0 Kelvin. And the upper band, that is what we call as the conduction band, consists of an infinitely large number of closely spaced energy states. And the lower band, which we call as the valence band, that consists of closely spaced, completely filled energy states when we discuss about the semiconductors at 0 Kelvin. I hope this is clear. So let's look at the energy band diagrams of conductors, semiconductors and insulators. That you can see this is the above part is the conduction band and the below part is the valence band for everyone. This diagram is for conductors, this is for insulators, and this is for semiconductors. So as you can see this at this position, let me see this, yes, that you can see this, that in this region valence band and conduction band are overlapping each other, or I should say it's an energy band between this two. Forbidden energy gap is 0 eV. That means all the electrons can directly commute from one band to another, and when they can directly or easily commute from one level to another level, that means they are always ready to conduct, and that is what conductor is all about. Yes. Now let's look at the insulators. Our valence band is filled with valence electrons, and conduction band is almost empty. Yes, so this is the valence band, and this is the conduction band. And as we have understood that valence band is filled with the valence electrons and conduction band is empty, as well as the forbidden energy gap is greater than 3 eV. That means when we say forbidden energy gap is greater than 3 eV, that means if you wish that this electron should switch to this, you must apply a large amount of energy to this electron so that it is having a capability to switch from the valence band to conduction band. So examples of the insulators, it's a wood, glass, etc. When we say it's a semiconductors, when we say semiconductor, it's a valence band is completely filled and conduction band is completely empty. But the energy gap between this two level is approximately 1 eV. And when I say approximately 1 eV or around 1 eV, that means compare with the insulators, a less amount of energy is provided to the semiconductors than the electrons that resides in the valence band can switch to the conduction band very easily. I hope this is clear. Is it clear? So forbidden energy gap Eg is less than 3 eV, and for germanium this energy gap it's a 0.72 eV, and for silicon this is approximately equals to 1.1 eV. So examples of the semiconductors are the germanium or the silicon. So I hope you understand that in the conductors the valence band are already, the valence band and conduction band are already overlapped with each other. So even at room temperature they start conducting. For the insulators there is a large energy gap between these two bands, and when there is a large energy gap between these two bands, that means it is almost impossible, or rather you need to apply a very large amount of energy to make them conduct. But for semiconductors, even a moderate amount of energy can do that electrons from valence band can switch to the conduction band, and that means they are ready to conduct. I hope this is clear. Yes. Now when we discuss the semiconductors, we are having two elements. One is the germanium, one is the silicon. Let's discuss that which one is preferred and why this is preferred. Let's have a look. So we have this two elements. One of them is the silicon, another is the germanium. The silicon is having an atomic number 14 and the germanium is having the atomic number as a 32. And as you can see that their last shell, yes, is having the 4 electrons, and this is the same case for both the elements. So at the room temperature we are comparing the silicon and germanium, that which one is preferred or what to do or which should be used. So at room temperature silicon crystal has fewer free electrons than the germanium crystal, and this implies that silicon will have much smaller collector cutoff current than the germanium. Second one, the variation of collector cuts off current with temperature is less in silicon compared to the germanium. And the structure of germanium crystals will be destroyed at the higher temperatures. However, silicon crystals are not easily damaged by the excess amount of heat that is going to be applied on it. But there is a one disadvantage for silicon over germanium is that the potential barrier of silicon is more compared to the germanium, and when potential barrier is more, then you need to apply a larger amount of energy to cross that potential barrier. And when you need to apply that larger amount of energy, that means you need to provide a supply of higher capacity. Next, so if we consider all the advantages and disadvantages listed above, we can conclude that silicon is the best element for the semiconductor devices and applications. And one more thing is that peak inverse voltage, which we generally call as a PIV ratings of silicon diodes are greater than the germanium diodes. One more thing is the silicon is less expensive due to greater abundance of the elements, and the major raw material for silicon wafer fabrication is the sand, and there is lot of sand available in nature. So even if we look at the cost wise, then silicon is the preferred material over the germanium. It is not the case that we only use silicon, but when and when there is a comparison between these two, a silicon is having a more number of advantages as number of disadvantages. I hope you understand this thing. Yes, so generally we prefer the silicon over the use of the germanium. But even I mention it one more time that it is not the case that we only use a silicon or we only use the silicon as a to manufacture a device from the semiconductors. I hope this is clear. Is it? Great. Now let's look at certain quick questions. So which of the following is correct? First, forbidden energy gap is the energy gap between valence band and conduction band. Yes, this is correct. Next, forbidden energy gap may be empty or may be partially filled with the electrons. No, this is just the energy gap. This cannot be filled or emptied. No electron will exist in the forbidden energy gap. Yes, this is correct. So answer should be this. It's a D. Both A and C are correct. Next, a valence band may be it could be completely filled or partially filled with the electrons. Yes, correct. It is empty or may completely filled with electrons. No, it is completely filled with electrons. No, it is empty. No, So this would be the correct option. I hope this is clear. Is it clear? Great. Do you have any doubts? Is there anything? Is there? No? Are you sure? Great and well done. So let's wind up the session over here. This is pure theoretical session of the semiconductors, but this was much needed, because when we used to discuss that what semiconductor is, we must understand that we are having the conductors, we are having the insulators. Why to choose the semiconductors? So this was essential to create and to build up a logic behind it. So revise it. I request you guys to please go through the NCRT of this unit as well. This will help us to have all those information which may be missed by myself. So please revise it as soon as we are moving ahead of this topic. There are much informations that has a written by an NCRT as a statements, and that can be asked by NTA in any of the examinations. So please go through it. This will help us to get good numbers. Thank you. Have a good day. Take care.